EDX Core Pure, Sequences in Series 2, Induction. An introduction to mathematical induction. Work out the first 4 terms of this pattern. What do you think the next term will be? And if you want to pause the video and try these for yourselves, you're welcome to. So the first one is a half. The second one is a half plus a 6, which gives me 2/3. The next one is a half plus a 6 plus a 12. It gives me, with the common denominator, 9/12, which is 3/4. And the last one is a half plus a 6 plus a 12 plus a 20th, which is 48/60th, and when it simplify it, we get 4/5. What do we think the next term will be? The question is, would it be add 1 to the top, add 1 to the denominator? To prove something in mathematics, you need to show that it is true for all possible cases. We could just check as many cases as we like, or we could use a computer to check a large number of cases, but this would still not prove the result. You might feel confident that the result is correct, but you would not have a full, complete proof. There are several methods of proof. There is proof by exhaustion, where you consider all the possible cases. You can't use this method if there's an infinite number of cases, but you could, for example, use proof by exhaustion to prove that 97 is a prime number. There's proof by deduction, where you use a known result to deduce further results. For example, we use the sigma r formula to deduce the sigma r cubed formula. There's also proof by contradiction, where you assume that the result is not true and use this assumption to deduce a contradiction to the original assumption. For example, there is a well-known proof that root 2 is irrational by first assuming it is rational and then producing a contradiction. So we suspect that the sum of this series is n over n plus 1. We could carry on checking for every positive integer, but we would never quite get to the end of the list, so we wouldn't be absolutely sure that there isn't a counterexample that doesn't work. We can't prove this result easily by deduction or contradiction, so we need to consider a new method. This new method is called proof by induction, and a simple analogy is to consider a set of dominoes that need toppling. What do you have to do in order to topple all the dominoes? There are 2 things we need to happen. We need to set up the domino so that every domino will knock over the next domino, and the other thing we need to do is to knock over the first domino. So we could think of this as 3 steps. Show that if the conjecture is true for an individual number, then it is also true for the next number. Check that it is true for the first number, and state the result is true for all the integers greater than the first one. In fact, we normally reverse steps 1 and 2, which wouldn't be very sensible with a domino analogy, but makes for a more straightforward proof in mathematics. So that is a simplified process. Step 1, check it is true for the first one. Step 2, show that if the conjecture is true for an individual number, then it must also be true for the next number. Step 3, state the result is true for all integers greater than the first one. So step 3 is our conclusion. So we're trying to prove that the sum of this series, which we've called Sn, is indeed n over n plus 1. So step 1, we need to show that the result is true for n equals 1. So let's have a look at S1. S1 would be 1 over 1 plus 1, which is a half. And if we look at S1 from the original series, S1 would be 1 over 1 times 2, which is also a half. So we now know that it's true for n equals 1. True for n equals 1. Okay, so always make sure you do that first step to make sure that the conjecture is true for that very first step, n equals 1. Step 2. We now assume that the result is true for n equals k. So we're going to assume that sk, which is the sum of the first k terms, will be k over k plus 1. So that is assumed to be true. We then consider n equals k plus 1, the next term in the pattern. So we have our assumption step, which is sk equals k over k plus 1. And we now need to show that sk plus 1 is k plus 1 over k plus 2. So assuming it's true for sk, it is also true for sk plus 1. So we start by considering sk plus 1. So sk plus 1 is the sum of the first k plus 1 terms of the series. So we've got to now rewrite sk plus 1. I can rewrite this now as the sum of the first k terms of the series plus that final term. And we assumed a result for sk. We've assumed that sk can be written as k over k plus 1. So that's my assumption being used. So what we've got to do now is to simplify this algebra and see what result we get. So going for common denominator, I get k times k plus 2 over k plus 1, k plus 2 plus 1 over k plus 1, k plus 2. Putting all of that over a common denominator gives me k squared plus 2k plus 1 over k plus 1 times k plus 2. And if we factorize the numerator, we get k plus 1 squared over k plus 1, k plus 2. And if we cancel down, we get the result k plus 1 over k plus 2, which is what we had to show was true for sk plus 1. So we've now used our assumption for sk to show that it is also true for sk plus 1. And there's the full method for you to work through. So we now know that if the result is true for n equals k, it would also be true for n equals k plus 1. So then we can come to our final step 3, the conclusion step. So if the conjecture or result is true for n equals k, then it is also true for n equals k plus 1. Since the result was true for n equals 1, it must be true for all integer values of n greater than or equal to 1 by mathematical induction. And this is a technique we'll be practicing in the next few sessions. So there is the process. Step 1. Check it is true for n equals 1. Show that if the conjecture or result is true for any individual number, usually k, then it is also true for the next number, k plus 1. And finally, your conclusion step. State that since the result is true for n equals 1, and if true for n equals k, it is also true for n equals k plus 1, it must be true for all integer values of n at least 1 by mathematical induction. In the next session, we'll be using induction to prove results about matrices.